And welcome to the third video in our series on semiconductors, and this time we'll be looking at a thing called the op-amp, or the operational amplifier. And this thing has been around for years. The very first one was made in 1941, like the transistor. It was made at Bell Labs, and it was made with valves rather than transistors, as the transistor just didn't exist at that time. What it is a DC coupled high gain amplifier, and it usually has two inputs, an inverting and a non-inverting, and the potential difference between the inputs is what counts. We also have very, very high gain, and we have to limit that gain. And there's a lot of theory behind this, and I'll deal with that in the handouts that I'm going to give you rather than on the film. We'll have a look at some of the more simple ideas, and we'll have a look at some of the practical circuits and see what we can do with this thing. Now, the op-amp we're going to be using is an 8-pin DIL package, the 741. It's been around for very many years, and it's the industry standard for a lot of things. It's a very good, very precise chip, and we'll be seeing a lot of it over the course of this film. So first we'll have a look at some theory, and then we'll get stuck into making some practical circuits and see what we can do with this useful piece of kit. Now, there are two basic ideas about the way you can work op-amps, and one is as the non-inverting amplifier. The op-amp here is hooked up so that the input is coming through to the non-inverting terminal. And the output's going out here, and we have a feedback with this 100k resistor and this 100k resistor as a voltage divider. Let's run it and see what happens. Okay, so we're putting 10 volts in there, but we're getting 20 volts out of the output, and that's because of this. You've got the equation here to tell you what the gain is going to be. The gain is equal to R1 plus R2 over R2. Well, you've got 100k and 100k, so that's 200,000 over 100,000. 200,000 over 100,000 is the same as 2 over 1, which is the same as 2, and that's your gain. 10 times 2 is 20. We can also see what we can make R1. So let's say we wanted a gain of 3. Okay, AR2 minus R2 equals R1. So 3 times R2 would be 300,000, minus R2 would be 200,000, and that's what we would put in R1. Right, let's stop the run, and we'll change this to a 200k resistor. And start the run again, and hopefully in the multimeter here what we should be seeing is 30 volts. Let's see what happens. Bingo. And it's the same for anything above unity, really. Let's stop the run, and let's say we want to put 15 volts there, which is a gain of 1.5. So what we'll have is 1.5 times 100,000, which is 150,000, take away 100,000, and that will give us 50,000, which should be the value of R1. So let's change it to 50,000 and see if we're right. 50k, and let's start running it, and bingo, 15 volts. However, it doesn't work for unity. For a unity gain it's a little different, because 1 times 100,000 minus 100,000 gives you 0, and when you start seeing zeros and infinities appearing, it's a sign that something's going wrong and you have to go back to the drawing board. Unity is very complicated with this sort of thing, and what we actually do for a quick way is divide R2 by 100, and if we do that, that will give us 1,000. So if I change that now to a 1K, and hopefully it will not give us quite exactly 10 volts, but it should be very near. Let's see. 10.1. That's fine, that'll do. That's great. Now usually people set op-amps up as inverting amplifiers for the simple reason that they're much easier to work with, and if we scroll across a bit, there we are, we've got an inverting amplifier, and you can see that the maths is much simpler. The gain, A, equals RF, which is up here, over Rin, which is here. And if you have the two resistors exactly the same, you will get a unity voltage. As easy as that. But I want you to notice something here. The voltage has a minus sign in front of it. It's inverted. It's an inverting amplifier. So, that's the basics of it. And let's see what we can do next. I think, to start with, we'll look at a thing called a summing amplifier. Now when we're doing electronics and we're dealing with parallel branches like these here with the switches and resistors, and the ends are all tied together to form one big node there, we run into a thing called Millman's theorem. And there's a lot of intense mathematics about this, but basically what Millman's theorem says is that instead of getting the sum of voltages that we'd expect from here, what we actually get is an averaging out. So, what I'm going to do first is I'm going to get rid of this line, and then I'm going to start the run again. We can see the multimeter up here. Zoom in a little bit. I'm going to click this switch so that it's closed. If I now put the multimeter on here, we'll see that we've got 1 volt. If I open this switch again, the multimeter will say 0 volts. Well, that's what we've expected to see so far. So closing this switch, the multimeter says 2 volts. Again, what we expect to see because there's a 2 volt supply rail coming down there. And on the same rail, there is the switch S3, 2 volts. However, what I'm going to do now is I'm going to close the switch S1 again, and if we were to sum up the voltages across here and across here, what we should see is 2 volts plus 1 volt, which is 3 volts, but we won't. We're actually seeing 1.5. Alright, so we're seeing 3 volts divided by 2 active branches gives us 1.5, the average. So if Millman is totally correct, what we should see is something like 1.7 if we close switch 2. And there we are. So, how are we going to set about overcoming Millman's theorem? Well, we're going to do it this way. And what we've got here is a couple of op-amps. And we'll stop the run a moment, and I'm going to put that line back in, because what it's doing is it's going from these parallel branches, which are averaging out, to the inverting input of the first op-amp here. Now, we've got a gain of unity here because we've got a weighted sum on this side and a 10k resistor on this side. We don't actually need a resistor here because this is doing the job for us. Let's see what happens in the multimeter when I do this. And we're getting minus 5 volts, and that's what the actual multimeter here is saying as well. So, this is an inverting op-amp. Okay, and what it does, it's a voltage amp, and it takes the weighted sum of the voltage here and outputs it here. If I click any of these off, the voltage here will change. 3 volts, 1 volt, no volts, 2 volts, exactly as we'd expect to see. But again, I want you to notice this minus sign, and the minus sign here as well. If we look at the other multimeter here, there is no minus sign. It's a positive going voltage, and that's because what we've done is we've taken the output from the first op amp and we sent it to the inverting input of the second op amp, and we've given it a unity gain again through these two 10k resistors. And again, if I click switches, you'll see the top multimeter, and if I move this multimeter over as well, everything changes. What we've got here is the basis of a rail splitter. So we've got, move the multimeter down a little bit, we've got positive going voltage here, negative going voltage here, and if I click where the ground is, 0 volts. And that way we can do a dual voltage supply to other op amps, or indeed, if you watched the video or read the handout on the video that I did for transistors, you'll know that CMOS transistors require either a positive or a negative voltage, and this is a way we can supply them with it. Now, as I said at the beginning of this film, we are going to be using LM741s for the op amp, and those are these things here. They are 8-pin DIL packages, and they're quite tiny. However, we are going to have a problem, because unlike some other operational amplifiers, the LM741 does not accept a single polarity voltage, so we can't use it directly with a DC power supply, or rather we can, but because there are bipolar junction transistor inputs in that thing, what it'll do is it'll float around the 2 volt mark even when there's no voltage applied to the inverting input. So what we need to do is we need to build something that will give us, from a single voltage, a dual voltage with both a negative and a positive going polarity, and that's what this thing on the breadboard here is. If I zoom in a little bit and angle the camera, and what we'll see is there are 2 capacitors and there are 2 resistors, and the capacitors are 47 microfarads each and the resistors are 10k each, and I will put this schematic in the handouts for this film. They're marked over with junctions, so you've got a junction here that goes to one end of the resistor and one end of the capacitor, and a junction here that goes between the two, another junction here at the bottom end of the second resistor and the bottom end of the second capacitor. So, what does it do? Well, here we've got a single polarity DC supply. There's the negative, there's the positive, coming into the breadboard. And what we need to do now is we need to get a multimeter up here and zoom out a little bit so we can see the figures properly, and we need to measure. Now the common ground is here, so if I put that probe on there and then that probe on there, and hopefully what we should be able to see get the probes on right. There we are, 4.48 volts. And on the other end, minus 4.48 volts. So, that side, we've got a positive going polarity, that side, we've got a negative going polarity. And the input supply itself is, of course, if I do this, about 9 volts. So what we do is we split that 9 volts up, and half of it goes to positive and the other half of it goes to negative. Now, let's move the multimeter, because to illustrate this point I have 2 LEDs. And they're biased in opposite directions, so one's forward biased and one's reverse biased. And what I need to do is, I need to put a wire in there, and a wire to the common ground of our little dual voltage supply here, and to the ends of the LEDs. And when I put this wire into that end, one LED should light up and the other stay dark, and when I put it to this end, the other LED should light up and the other should stay dark. So let's see what happens. Oops, the wire's in properly. There we are. Okay, so this LED is lit and this LED is dark. Happens when I swap the ends. This LED is lit and this LED is dark. Let me zoom in on that so you can see the LEDs properly. And I'll just bend one down a little bit. So, the negative end, this LED is lit, and at the positive end, this LED is lit. If you can see that properly. There we are. Do it again, just to make sure. One lit LED, and the other lit LED. So we can say with some certainty that that's working, and now we can get rid of the LEDs and attach one of the LM741s to it and see what happens. And prototyped up on the breadboard here, we have our little summing amplifier, and if I just move the multimeter out of the way so we can see a little bit better what we've got, and zoom in. So, we have the LM741, that's this chip here, and this is pin 1 at this corner, and at pin 6 here I have an output, and from the output there is a feedback resistor going all the way round, and that goes back to the inverting input. Excuse me. And the non-inverting, the non-inverting input has been tied to ground here, and from here, zoom out a little, from here we have our power supply. I have a hook running down, and that's going to V minus. That's the negative end of our power supply. So I also have the positive end of the power supply going down this rail, and here, by this green wire here, it's feeding V+. Pins 5 and 7, pins 5 and 8 are not connected to anything at the moment, and neither is pin 1, and that's because pin 1 and 5 is the offset null and we don't need to use it in this circuit, and pin 8 on this chip is not connected. Moving around a little bit and zooming in again, and what I have here is a voltage divider, and that voltage divider is taken from the power supply and it's feeding to these buttons. And what I'm hoping is that each of these buttons will have an equal output, and when I press one it will show me that output, and when I press a second it will show me the same output, and so on and so on. But when I press all three it will show me the sum of that output. And you'll see these resistors here leading back up to the amplifier are the same value as the feedback resistor, as we saw in our drawing. Well, let's zoom out, put the multimeter into the picture. Zoom out a little bit more. And what I shall do now is I shall press the first button. That tells me 0.36. You can't quite see that. Again, that tells me 0.36. And the third button tells me 0.362. So let's press two buttons, the top two. Now if it was summing perfectly we would expect to see 0.72, and it's saying 0.68. It has lost a little bit somewhere, and it's probably due to the fact that I'm losing something by using two buttons at the same time. 0.36 should give me 102, and it probably won't turn out to be that, but it will probably turn out to be close, so let's see what we've got. Pressing all three buttons. 0.9594, can't quite make up its mind, 0.9594, somewhere around there. So we're getting the sum of all three buttons. If I let that one go, back down it goes. If I let the second one go, back down it goes. If I let the first one go, back down it goes. And that's working. And now the question is, what can we do to make that useful? Well, what we've actually built here is a 3-input gate, and we can use this as an AND gate. And what we're going to do next is we're going to attach it to a microcontroller and see if we can get it to work the microcontroller. Now, the operational amplifier is a device that was used in analog computing, and that's where it started life. And what it could do is it could take signals and it could amplify them if you had a very weak signal. It could multiply them, sum them, subtract them, and it could even make a clock, and we might have a look at that later. Of course, analog computing is obsolete now. Nobody uses an analog computer anymore, and the operational amplifier lost a lot of its role in life through that. But it's such a useful device that it's still around in everyday electronics, and what we're going to do here is we're going rather back to its roots, because this thing here is an Arduino microcontroller. And as I've said before, a microcontroller is a curious blend of computing sciences and electronics, and it features largely in a discipline known as physical computing. If we look at the op-amp circuit for a little while, we'll see it's exactly the same thing. So here I have my operational amplifier, LM741 chip, and the feedback resistor, and I have three inputs here set up to go to the inverting input as a summing amplifier. Excuse me. The difference this time is I'm taking the signal and I'm sending it not to a multimeter, but I'm sending it to the analog reading pin of this microcontroller. And if I zoom in on that, angle the camera a bit better, there we are. And that's what this green wire is doing. So there we are. There's the analog input. There are 6 of them in total. That's going to be important later, we'll find out why. Now, the idea here is that I've got these 3 inputs, and if I press any one of the inputs individually, nothing happens. If I press any 2 of the inputs together, still nothing happens. But if I press all 3 inputs at the same time, the LED attached to the microcontroller lights. If I take one input off, And it doesn't matter what combination I do. As long as all three inputs are high, then I get the LED lighting. Now, of course, in this occasion it is an LED lighting, but it could be other things. You could use it to drive a motor, and in machines where synchronicity is important, you see this sort of sensor all the time. So a signal will come in, oh, that's ready. Another signal will come in, oh, that's ready too. And another signal will come in, right, that's ready, let's do something. You might ask what the advantage is. Well, earlier you might remember me saying that there are 6 analog inputs to this. And what I've done here is I've taken 3 input signals and summed them up through the operational amplifier so that I only use 1 analog input on the microcontroller. And that's one advantage of using this thing. It saves me a lot of space on there. I could of course buy a bigger microcontroller. This one I can buy for £15, and the smaller versions between £3 and £5. However, if I wanted something with more analog inputs, I'd be looking at upwards of £40. So, by summing up all the analog inputs I need with the operational amplifier and sending the resulting output to the microcontroller, I've managed to save 2 analog inputs, which I can use for other things. Now, the LM741 is a very versatile chip, and what we're going to do with it now is we're going to make a form of oscillator. And this is a relaxation oscillator. It's an astable multivibrator, and the reason it's astable is because there are 2 states the voltage can be in, and it's not happy in either of them and flips between all by itself. And these are the states: up, down, up. And that's one whole cycle of the waveform, and as you can see, it is a square wave. So we're going to get to how it does this, and this is rather complicated. So what I'm going to do is I'm going to go through it quite slowly, because if I don't, I'll probably end up confusing myself with it as well. So what we've got is we've got a voltage divider here and a resistance capacitance circuit here. The voltage divider gives out a voltage at the junction here, which we'll call B, depending on the ratio of these 2 resistors, and that voltage goes around to the non-inverting input, and that's what we use for the reference voltage. Now when we start it up, this will be saturated, and what will happen is it'll take from there through that resistor and charge up the capacitor to the voltage of that rail through the capacitor and resistor's time constant, which is the farad value of that times the ohmic value of that. Now the capacitor wants to charge fully to the voltage of V out, and that will take 5 time constants, and it'll still not be charged fully. It's rather like Zeno's paradox. It doesn't actually charge fully ever, but it can be said to be as near as full as to make no difference after 5 time constants. However, as soon as the voltage coming from here is equal to or greater than that coming from the voltage divider, the op-amp will change state. Down it will go. The capacitor now sees that change in state and will start to discharge. As it's discharging, the voltage there will drop until it gets to a lesser state, in which case the op-amp will change state again, and the whole cycle carries on like that. Well, we see that there are two equations that govern this thing, and the first is to do with the voltage feedback B from the voltage divider to the non-inverting input, and the second is the time, and that's to do with the capacitive circuit up here. There's R1 and there's a capacitor, and as you'll see it's 2RC log natural 1 plus B, 1 minus B. So, let's do B first. Now, most designers will go with a trick here, and what they will do is they will get B to as close to 0.462 as they possibly can. And there is a reason for that, and the reason lies over here. Now, what you could do is you could put a 30k and a 35k capacitor in there, and that would give you very close to 0.462, but they're not standard values. Now, the reason we want to get to 0.462 is because of this log natural here. So, if we have 1 plus B and 1 minus B, then we get Mr. Calculator on the job. Okay, B is equal to 0.4621 plus 0.462, 1.462 as we thought, and 1 minus B .538. So let's put that in the memory and put back in 1.462, and what we'll get if we divide that by that, 2.7174, and so on and so forth. If we take the log natural of that, we end up with a figure so close to 1 that it makes no difference. And what we can do there is we can say T equals 2RC times 1, and anything times 1 is itself, so we can take that to be T equals 2RC. Well, that's good. So if T equals 2RC, what we can do is go back to our circuit here, and now let's pick a nice big value for our capacitor, 470 microfarads. Now, 470 microfarads works out to 0.00047 farads. So, clear that. 0.00047. Now, these three zeros here are interesting, because if I multiply by 1000 I'll get 0.47. Were I to put a 1k resistor in, so multiply that by 1000, 0.47, I would get that bit of the cycle lasting for just shy of half a second. But of course the equation is 2RC, so we multiply by 2, 0.94. So I would get something that did that for just shy of a second, and that would be a frequency of round about 1 Hertz. If we go back a bit, 0.00047, and let's say this time I want the actual mark time here to be 1 second. And I'm going to use a 2.2k resistor, 2200, 1.034, and of course times 2. So I've got the thing here that lasts for 2 seconds, and the mark time should be 1 second, and the space time should be 1 second. Well, let's build it to those specs and see what we get. Well, we've had a look at the theory, but as we know all too well, theory and practice don't often accord with each other, so let's see what we've got here. As you can see, the thing is blinking along. Just switch it off and switch it back on again. There we are. And let's zoom in and see what we've got. So, if I move the camera around a little bit so that we can see things. And here, for the voltage divider, I've used a couple of 3.3k resistors, which gets me very close to that 0.462 we talked about in the theory. And over here, for the feedback resistor, 2.2k, and the capacitor is 470 microfarads. Now, as you can see, both the mark and the space-time are roughly 1 second. Let's do something interesting and change the resistor here for this potentiometer and see what happens. And we're blinking a little more slowly, but if I turn the potentiometer, what I can do is change the rate of blink, so I can make it a lot faster, or I can make it a lot slower, depending on what I want. But you'll see in each case that the mark and the space times, i.e. the time that the LED is on and the time that the LED is off, are equal. So, there is a reason for using this LED here, and the first reason is the obvious one, in that it's a visual indicator and we can see what's happening. The second reason is not quite so obvious. If I use an LED here, what I can do is I can plug something in to tap off when the LED goes either on or off. And I can use that to detect a signal on the rising or the falling edge of the LED and send it somewhere else. And in that way I won't overload the output of the LM741 with anything too resistive at the other end. And that's really it for the A-stable. And we'll have a few concluding words and we'll wrap this video up, and we'll do a fourth video which brings the diodes, the transistors and the operating amplifier all together in one big circuit that does something useful. So in this video then, we've used the LM741 operational amplifier. We've used it as a summing amplifier and we've used it as an oscillator. We haven't actually done much amplification with the thing, but hopefully we'll rectify that in the fourth video of this series, in which we're going to build a radio circuit, a tuned radio frequency receiver. So we'll close this film here and we'll have a look at what comes next.